Hello, my name is Sajjad Bhatt and welcome to the course on strength of materials. In this video, we will be looking stress strain curve for mild steel. But before we proceed, I will briefly explain you the concept of stress and strain. Then we will also see what is mild steel. Then we will follow our video with an experiment where we will exactly obtain the stress strain curve for mild steel, and on that basis of experiment we will draw some conclusions and we will discuss the details of this particular curve for mild steel. All right. So first of all, what is stress? And when I talk about the stress, I'm not talking about the mental stress, I'm talking about the physical or the engineering stress. All right. And in order to understand the concept of stress, let me just give you a very brief analogy. Say, say we have a prismatic bar. Prismatic, I mean a bar, a solid bar having uniform cross section. All right. Say of length L naught. Now, this body is under equilibrium and it is stable in its, that is in its minimum state level of energy. All right. Now what if I apply some force P naught, and let's suppose this force is uniaxial. That means this force P naught is acting in one direction only or in one axis only. So what happens is this body will then get stretched under the application of force P naught, and this body will get elongated or it will get stretched like this. All right. And then this L naught will turn out to be L1 under the application of what? Under the application of this force P naught. Now, if I ask you again, is this body under equilibrium? Now, at this point of time, this body will try to regain its original position. And why this will always try to regain its original position? Because here the internal forces comes into picture. And what are those internal forces? For that, let me just cut a section. Let me just cut a section AA. And once we will draw a free body diagram of this section AA, we will be having like this. Let me draw it with white color. We will be having section AA like this. All right. We will be having a section A like this, and then we had a force P naught like this. And now what happens is internal forces comes into picture, and these forces will be within the particles, within the material itself, and these forces these forces will try to counteract the force P naught, and again in this direction also there will be the counter reaction by the particles for the force P naught. All right, for this force P naught. All right. So these forces, these internal forces which I am highlighting, all right, so these forces will always try to counteract the force P naught, so that this body gets in its minimum state level of energy, which was this position. All right. So why it happens? So because in order to come again under equilibrium. And these internal forces which develops within the material will always try to counteract these forces. And these forces, since they are distributed over an area, we say phlogistic forces. That means internal forces, or internal forces, or internal forces distributed over an area, say AR. We say this is stress, denoted by sigma. All right. Or you might have observed, in case of a rubber, say we have a rubber, say we have a rubber. If we try to stretch this rubber, all right, this rubber will get stretched, all right, and this rubber will always try to regain its original position because of its internal material, because of the elasticity, because of the internal forces which develops within the body, and it will always try to be in its minimum state level of energy. And it happens so that this body, the internal forces which counteracts these external forces, and finally if we remove these forces, the body again turns out to be in its original state. All right. Now, this was a very simplistic approach in order to understand the concept of stress. But what if we had a body, say we had a body, all right, and what if I apply some force P1 in this direction, and P2 in this direction, and P3 in this direction? Will the stresses be the same? That is, will the stresses be normal only? The answer is no. So in order to understand this, what we have to do is just take a very small element, a cubical element we will take out of this body, and we will realize its effect. All right. And in order to do that, so just let me draw this small cubical element in this way. All right. And now let me draw a frame of reference like this. Call this axis as x-axis, call this axis as z-axis, and call this as y-axis. All right. Therefore this plane will be x plane and having cross-sectional area of A. Cross-sectional area of A. And this plane will be the z plane, again having cross-sectional area of A, because this is the cubical element. All right. And this will be called as y plane. All right, having cross-sectional area of A. All right, cross-sectional area having cross-sectional area A. Okay. Now, in order to get the general stresses under these loading conditions, what we can do is, see, since we had a body having force P1, having force P2 in y direction, having force P3 in z direction, what it did is we took a small element and we have shown it here. All right. and we have this blue colored as x plane, this yellow color as z plane, and the green color as y plane. And what will happen is, like, in the x direction we will be having, since there is a force P1, this force P1 will lead to P1 by A. That means it will lead to normal stress sigma, which is in the x direction. Okay, again we will be having P3 over A. Alright, this A is this A. Alright, and this will lead to normal stress sigma Z. Normal stress is a stress which is acting normally, that is perpendicular to the plane. Alright, and so this will be as sigma Z, that is normal stress in the Z direction. And again we will be having P2 by A, which will lead to a normal stress in the y direction. Now what if I ask you, will there be the effect of one force, say force P2, will there be the effect of this P2 on a plane which is in the x direction? The answer is yes. There is inter-level interaction, there is inter-level influence on other planes. That means these forces will be having the effect on other planes as well. Now suppose since this P2 is acting in the upward direction on the y plane, so we had a normal force of sigma y. But on this plane, this is not acting normally. So this P2 is not acting normally on the x plane. This is acting along the cross section. This is trying to get upwards along the cross section. So therefore it will try to generate a shear stress. So it will be like P2 over on plane x, it will be like P2 over A, and will lead to a shear stress on x plane. And since this is due to the P2 is in the y direction, therefore we will write as tau x y. All right, and again P3 was acting normally in the z direction, therefore we had sigma z. But on x plane it is acting along cross section. That means we will be having P3 by A, and this will lead to a shear stress tau, which is acting in the x direction, but it is due to the P3 which is acting in the z direction. Therefore we will be having tau x z. All right, and similarly we can draw this small element, like we can have a stresses under general loading conditions as this is a small element which we have three normal stresses. All right, this was sigma x, this was sigma y, and this was sigma z. All right, and we had this a shear stress, that is tau was in the x plane and due to y. All right, and over here again we had tau in y plane due to x, and here again we had tau in z plane due to x, and again we had tau in x plane due to z. All right, and over here we had a shear stress of tau in z plane due to y. All right, and over here again we had a shear stress of tau in y plane due to the force P3 which was acting in the z direction, therefore z. All right, so this is something what we call as stresses under general loading conditions. Very important concept. All right. So in order to summarize this, so whenever we will see a stress, we will be having only two types of stresses. One is the normal stress, which is acting perpendicular to the plane, and we had sigma x, sigma y, and sigma z. And again we have the shear stress. And how many stresses we had under general loading condition? We had 6 shear stresses, that is tau. So one was tau x y, tau x z, then again tau y x, tau y z. All right, and again we had tau z x, tau z y. So these were the general stresses. Okay, and normal stress is always denoted by sigma, and shear stress is always denoted by tau. And in order to summarize, we can have like this. Say this is sigma normal stress, and this defines the plane, this defines the direction. All right, again this will define as plane, this will define as direction. Since we write sigma xx, when we write say for example we write when we write sigma x, it automatically means sigma xx. That means this is plane x in acting in the x direction. All right, and let's suppose sigma zy, tau zy. That means tau is acting in the y plane in the z direction. So this is very simple. And also let me tell you, same happens in case of a strain. But before we go ahead, let me tell you what is strain. Strain is nothing but it is a measure of deformation of a body. It is a measure of deformation of a body. What does that mean? For example, I had a body, say of length L0, and let me apply some force P0. This body will get stretched to L1, being L1 greater than L2 under the application of this force P0. So how we define is we defined strain as the measure of deformation of a body. That means how much the body has deformed. Therefore, we can write L1 minus L0. How much it has been deformed? L1 minus L1 minus L0 over the length, over its original length L0. This is how we define strain. That means change in length per unit length, or change in dimension per unit dimension, is nothing but the strain. It is a dimensionless quantity of order 2 tensor quantity, that I will define further, and that I will define in the preceding class. All right, now see, there is no such direct method by which we can calculate the amount of stresses developed within a body, but we do have some techniques, we do have some devices which can measure the amount of strain attained, and those devices are called the strain gauges. Those devices are called the strain gauges. And the working of these strain gauges is very simple. They are similar to the adhesive tapes. The working is very simple. Let me brief you. Say, for example, we have a body, and what we do is we stick these strain gauges onto the surface of a body, and these within these strain gauges there is a thin wiring, all right, and this wiring is attached to some electronic circuit IC, etc., which is programmed and calibrated. And once, say, this was of L naught length, and once we try to stretch this body by the application of force P naught, this body gets elongated, all right, and this length turns out to be L1, and then these strain gauges also gets stretched, and the wire also gets stretched, all right. And we know the concept of electrical resistivity. Once you stretch a wire, its electrical resistivity changes, and once electrical resistivity changes, we are able to measure that change by these electronic circuits. And after that, there is a calibrated program, and accordingly we can calculate how much resistivity has been changed, and accordingly we can see how much the deformation of a body has happened. Okay, so this was all about the concept of stress and strain. Now coming to the mild steel. What is mild steel? Mild means gentle or present in a lesser amounts, and over here this mild correlates with the carbon. That means carbon which is present mildly, that is present in a lesser amount or in a very minute amounts, and usually the variation is like 0.05% to 0.25%. All right, so that means a steel having carbon of percentage 0.05% to 0.25% by weight, which is very important, by weight. All right, by weight. If this is the amount of carbon present in a steel, we say it is a mild steel. The advantage of it is like if you add more and more carbon, the steel gets brittle, and if the carbon is present in lesser amounts, that means it will be ductile, and carbon actually enhances the strength of a steel. And since we have lesser amounts of carbon, therefore our steel will be ductile, as well as since carbon is present, therefore there will be the strength also. And this gives us the advantage, like we can use it in automobiles. We can use it as a structural steel. There are so many other advantages also, but these are the two uses which I am mentioning over here right now. So this is all about the mild steel. And let me tell you, we do study the mild steel, we do study the stress strain curve for a mild steel, and usually we don't study the cast iron steels, etc., and other materials in our syllabus, because mild steel is the one which gives us all the properties, or all the terms which can happen in any other state, in any other stress strain curve. Therefore, now let me proceed with the experiment where we will test our mild steel in order to obtain the stress strain curve. So, therefore, let me just show you the specifications of a specimen which we take in our experiment, and then we will proceed accordingly. So, this is what I have written. The definition of stress, definition of mild steel, and now let we proceed to the specimen. See, over here we take a specimen as a solid cylindrical rod, all right, and we prescribe the gauge length as 2 inches. This is the gauge length because over here we do have some threadings. All right, this is a solid cylindrical rod of gauge length 2 inches, and this way we actually can generate a uniform stresses happening within the gauge length, and the middle diameter we prescribe as 5 inches, and L by D. L means gauge length and D means middle section diameter, and it should be within 4, not within 4, it should be exactly 4. All right, now let's proceed with the experiment. See, this is a mild steel specimen, and this L naught has been represented as a gauge length, and D naught is the diameter. And this machine is called the Instron machine or the Universal Testing Machine, UTM. And this is the insertion of this specimen. So what this machine actually does is it gives a tensile force to this specimen, and there are strain gauges fitted also. And now we have this program which gives us the position, that means the strain, and this is the force. All right, force means stress because by the help of force we can get the stress, and this is the elongation, that means this is the this way we can get the strain. And you can see the curve has been generated because we cannot observe this tensile forces actually acting, but after it attains the plasticity you can see the specimen getting stretched. All right, this is the curve which is obtained, and this is called the necking because the diameter gets drastically reduced and the specimen has failed now. And this is the very basic curve which we got under the application of the tensile force, and this is the what we called it as a stress strain curve for a mild steel. And this point we can, or let me draw a very practical curve which we can understand. See, this is something which we can draw. All right, this point, say suppose this is point A, say this point is B, say this point is C, say this point is D, E we call this point as F, G, and G we call it as a fracture point, and this point we call it as ultimate yield point, and this is we call it as the proportionality limit point. This point B is called the elastic limit point, All right. C is called the upper yield point, and D is called the lower yield point. Okay, so now let me show you this figure like this. So this was the proportionality limit and the uh, elastic limit, and this was our starting of the strain hardening. This is the ultimate yield point, and this is what we call it as a fracture point. Now, in order to discuss its details, let me show you in the other figure.